Okay, okay, okay. Wait.
We
मानव
are
कहाँ
live.
है? मानव है?
We are live. मैं हूँ.
Okay. Hello, friends. Welcome back to the virtual meetup by ILUG-D and SSC. Hope you are doing well at your homes. I am Shivam. I welcome you here. Thanks for joining. So, we had awesome talks before. So, this is our calendar on 4th, 5th, 8th, 11th, and 12th. So, this talk is by Manav, who is first year student at uh, Maharaja Agar Singh College. So, this is a series of meetup by ILUG-D and SSC because of the lockdown, and this is the eighth one. Also, we have awesome calendar. You can find uh, the link of the calendar in the chat window. Also, we are planning some, some non-tech sessions like how to make coffee and momos at home. Yeah, so we are using Jitsi because it's free, and if you have any other suggestion, you can write it down on the Telegram group. Also, we are hosting some quizzes at Kahoot, which is awesome, and the quiz winner will get this awesome plant. So also we are live on YouTube also. You will get the link in that left side chat window. So yeah, you can connect with us on Twitter, and we are on Telegram as well. Yep. So this is our meetup.com link. So yeah, if you are part of any meetup organization, we are open for collaboration. So yeah, I am going to hand over this to Manav. So hi Manav,
Hey everyone. So,
how are you?
Sivam, should I start?
Yeah.
Please raise your hand if you can see my screen. Anyone? Okay. So I see a couple of hand raises, which means you folks can see my screen. So let's begin. So, Sivam, thanks for the introduction. Good afternoon, everyone. I'm Manav. I'm a first year student at Maharaja Agri Institute of Technology, and I'm trying to learn how computers work every day. That's it. So today we're going to be talking about making Arduino boards talk. Now, a lot of people have interpreted and misinterpreted this topic, but today this is going to be about different communication protocols which we can use to make, like, to actually communicate between two or more Arduino boards. So, without any further ado, let's get to it. So, first of all, let's discuss what exactly is a communication protocol. So, a communication protocol is a defined set of rules and regulations for maybe two or more entities which want to communicate amongst one another, and they can communicate using those rules by changing some physical quantity. For example, in case of wired protocols, we're going to see that it will be voltage. In case of wireless, maybe vibration of electrons, maybe vibration of air. So that's the physical medium. Now, what is the need for communication? So I'm just going to pick out a couple of examples which I have faced wherein I needed to make two or more microcontrollers communicate amongst each other, and I had to think a lot about which protocol to use and how to implement it. So the first example goes back a couple of years when I had to build, I think, a small device. So the form factor was very limited. Naturally, the only microcontrollers for prototyping that come to mind are maybe Arduino Nano or Arduino Micro. So, which simply means that I'm pretty limited in the amount of maybe digital pins that I can use. So, a typical Arduino Nano has 14 digital pins for me. Let's say I connect a LCD display in 8-bit mode. So, 8 of those are gone. Let's say I connect another peripheral or maybe sensor that utilizes 3 more pins, and boom, I am left with almost no pins at all to connect new things. So for that, I need another board, and somehow I need to make those two communicate amongst each other so that things can go properly. So this is one case. Another thing that happened to me very recently was that I was a part of team and we had to build a kind of a soldier suit for Indian Army soldiers. So it had like 5 7 features in it. So like it was a team of 5 people. So all this work was distributed amongst the people. So everybody was using their own microcontroller. It was an Arduino since we were prototyping. So everyone was using their own microcontroller. In the end, when we had to compile the entire thing, so we were faced with two different options. One thing was that maybe we could put everything, we could take all the code, compile it into one single file, put it up on a maybe a mega Arduino mega so that we have more pins, or maybe we could keep it modular, simple into different fragments, and all those fragments could send data to one master Arduino that could interact with the outside world. So we chose the second way because it seemed simpler at the time, and there were a lot of implementation details which were to be thought of for the first option. So that's the need for communication. Now, today we're going to be talking about wired and wireless protocols. So, as the name clearly suggests, wired protocols mean protocols that require me to connect with wires, and wireless protocols are protocols which do not require wires. So, further, we're going to be talking mainly about wired protocols today, since all of these wireless protocols that I have listed right here, these are the mainstream ones. I need everyone to note that these are not all the wireless protocols, but these are the mainstream ones that we use. So the wireless protocols that I have listed here, all of these require separate talks of their own, and they're actually very huge topics. So that's something. So today we're going to be talking about wire protocols only. So under wire protocols, we have two main categories: serial and parallel. Now, the name tells us that parallel protocols use different pins. So let's get to how these are implemented. So this is what a parallel protocol implementation looks like. So this is the transmitter right here. We have a receiver, and let's say I have to send out these 8 bits. So what I'll do is I'll maybe send out a single clock cycle, and all of these bits are sent in a single clock cycle. So it seems fast, but the problem occurs when I have to send more amount of data. So let's say these are 8 bits. Let's say I have to send 16 bits. So all of my digital pins on a typical Arduino are hogged just for communication. So I cannot, this is not actually viable for real life solutions. Then there is serial protocol. So in serial protocol, let's say I have to send out these 8 bits. For sending these 8 bits, I need 8 clock cycles. So a single bit will be sent out in one clock cycle. Now, this seems slow at this point, but there are ways to actually boost it up, and we're going to talk about them today. So this is what a serial protocol is. Now, I'll just stop right here and let's take some questions if you folks have any. So, seeing no questions, I will move forward. So, serial protocols are further of two main types: synchronous and asynchronous. So, the name tells me that synchronous protocols mean protocols that require a clock to be sent out. Now, typically, when we think of a clock, we think of maybe something round which has hands which move. But this is not the clock we're talking about here. So, the clock we're talking about here looks like a square wave. So a square wave kind of clock needs to be sent out, and for that we need an additional clock pin, which is generally represented by CLK, and we're going to have a data line. So that is a synchronous protocol. For asynchronous protocol, we do not need to send out a clock. There are ways by which this communication takes place without sending out a clock in asynchronous protocol. So let's talk about them first. The first protocol we're gonna get into is the UART protocol, which stands for Universal Asynchronous Receiver and Receiver Transmitter. So this is what a typical UART communication looks like. So in UART communication, we need to send out three different things before we can actually start sending the data. The first one is the length of the data. This is not compulsory, but a lot of microcontrollers send this. Then we need to send how the start and stop bits will look. This is also not compulsory, since a lot of microcontrollers have a very fixed implementation and we have to, a lot of times we're restricted to that, but not all the times. So that's that. And the third thing which I've not mentioned here is the baud rate. So a baud rate basically means that we need to tell the other microcontroller that in how much time the first bit will be sent. Since we are not sending out a clock, so the other microcontroller needs some way to know that we have, like, some way to know that when one bit will end, when the other will start. So for that we have the baud rate. Now let's begin with the implementation details. So we have a transmitter and a receiver. Now when we want these to start communicating, so the UART data line always stays high, it is always 1. But when we want them to start communicating, we set this data line to low, so that the other microcontroller knows that now I will start receiving data, and we tell it what the baud rate is going to be. So a very common baud rate is 9600 bauds per second. Let's demystify what 9600 bauds per second stands for. So it simply means that a single bit will be sent out in 1 upon 9600 seconds. So that means 104 microseconds. So now the other microcontroller knows that as soon as I see the first low, I need to count for 104 microseconds. Then I'll know that the next bit is going to start. So this is what it looks like. We have 100, and so as soon as this low is triggered, the microcontroller starts counting to 104, reaches here, sees the first bit, and then again starts counting to 104, reaches here, reads the second bit, and so on. But this actually looks very, the implementation shown here is a very ideal case scenario. This is not exactly what happens every time. So whenever this shift or trigger, let's say, takes place between 0 and 1, there's always some kind of uh how do I call it, data, like it's similar to the case of button debouncing. So it does not become 1 instantly, it needs to take some time to stabilize. So that's that. And we have, so what happens is, instead of reading from the beginning of this bit, it waits for about 52 microseconds, which is half of 104. It waits for 52 microseconds, counts up till here, then starts reading the bit, so that it can account for the instability. Then it counts for another 52 microseconds, and it knows that the first bit has ended. Now it waits for another 52 microseconds, reads this bit, counts for another 52, reaches here. And this is how this protocol works. So let's discuss about how this works specific to an Arduino. So in Arduino we have these pins, TX and RX pins right here, which are 0 and 1. Now the catch here is that, like, this is a very good thing maybe in Arduinos, that we have this single port USB port for both serial communication to the computer, and this port is also used for powering. In a lot of boards, this, like, we have a single port for powering and another port for serial communication. So this port is internally mapped to both of these pins. So whatever data is written to this port is written to these pins. So if we are uploading a program to the Arduino, we should never actually have anything hooked up here, because it can and it will cause program difficulty in program uploading. We'll see errors from the IDE saying maybe programmer not found or something. So this is how it works in case of an Arduino. And now why is this ground connected to this ground? So let's discuss one very important thing in case of wired protocols. It is that when two or more peripherals are connected by using wired protocols, we always need a common ground. Now why is that? Let's say controller A is connected to a battery which thinks the ground is 0 volt, and let's say controller B is connected to a battery according to whom the ground is 2.5 volts. So the initial microcontroller sends a 0 volt pulse. The other microcontroller won't know what that means. Right. So we need a common ground between both of these controllers so that we can establish the fact that what is 0 and what is 1 for easy communication. So this is what it looks like. Now let's get into the code of how this works actually in case of an Arduino. So please raise your hand if you can see this screen. Yeah,
Can
I
you
see a
please
couple of hand
zoom
raises.
it?
So let's get to it. I think the font is big enough, right? Again, I need a hand raise to verify.
Yes, it
Nice.
is.
Okay. So first of all, we're gonna have to include this library called software serial. So what the folks at Arduino have done for us is that for most of these protocols, we don't actually need to delve deep into the implementation details to actually write code for this. All we need is our simple libraries, and they've implemented most of the functions for us. So we need very simple tidbits of code. Now I would like to get into something this about this software serial library. So I last thing I talked about was the TX and RX dilemma, that we should not connect any pin there while trying to upload a code. After the code is uploaded, we can do that. But to prevent that, we have this library called software serial. So what software serial does is that we can specify any two pins to this object right here, and it will convert that into a UART port for easy communication. So we won't have to plug out our circuit every time we try and upload a code in the TX and RS pins. So like I have mentioned here in the comments about how this object is initialized. So the first pin is the RX pin, the second pin is the TX pin. This is an object I've declared right here of the software serial class. Now let's get to the setup. So serial.begin, a standard line for serial communication to begin between our computer and Arduino. Now this is soft serial.begin, which means serial communication between Arduino, master Arduino, and slave Arduino. So currently we're talking about the code for the master Arduino. So this is what it looks like. And then it's just going to write whatever it is reading from the serial port, that is from my computer. Serial.read is from my laptop slash computer. So whatever it is reading from this serial port, it's going to write to the soft serial port, which means to the other Arduino. So this is how the implementation looks like for uh, the master UART Arduinos. Now let's see the slave side. Okay. So on the slave side, all we have is this simple program wherein we're defining this LED. Now this is not important. The LED part is not important. What's important is reading this why while this port is sending data, and read this into a buffer. That's it. So any problems or doubts in this? I'll wait for a while. You can just unmute yourself and speak if you want as well while I'm waiting. Yeah, Nikhil, you can speak.
Yeah, so you was telling about UART and all. So I just wanted to ask, is UART reliable way of transferring data between two microcontrollers or something like that? Like if this electronic surge or some kind of glitch, then how are you going to tackle that?
Yeah, so we do have acknowledge pins to prevent some things like electronic surge. So what acknowledge now acknowledge pins are present in the recent microcontrollers which ship with UART functionality. So what happens in acknowledge pins is that once the other microcontroller is cleared to send data, then only the data will be received. So that depends upon me whether I want the other microcontroller to send the data. But yes, there are security vulnerabilities in this as well as there is in other protocols.
I was not talking about that part. I guess my question was somewhat unclear. Basically, what I was saying is, for example, I'm sending 16 byte of data, for example, just
Okay.
so like uh, like after 12 bytes or something, there is an electronic search or there is a electronic interference would be a great word. There is an electronic interference that somewhat changed or corrupted the data. Then how are you going to tackle that situation? uh, am I supposed to transfer the data again? Is this some kind of CRC thing or something else?
So for that, I believe it would depend somewhat upon what microcontroller is on the other side. So let's say if some microcontroller is built in with the functionality of actually handling UART communication errors or problems. So we can have that. Other than that, what you're talking about is something I've not considered yet, but maybe I will
Sure,
in
it's all.
future projects.
Let's continue with the talk.
Sure. So, any other questions? The floor is still open. Okay, so seeing no questions, I'll continue. So, next up, we have the serial peripheral interface or the SPI protocol. So, SPI is a very popular and fast protocol which has a lot of advantages and disadvantages. So let's straight get to what SPI is and how we can implement it. So SPI has 4 pins. Currently I've shown only 3. I'll discuss why so. So SPI has 4 pins. Now we are getting to the synchronous protocols. So SPI is a synchronous protocol, and the next protocol we're going to talk about, I2C, is also a synchronous protocol. So both of these pins will need to send out a clock. That is something we need to remember. So both of these pins will need to send out a clock. And in SPI, we have master out, slave in, and master in, slave out, which are abbreviated as MOSI and MESO pins. Along with that, we have chip select pin, using which we can select the slave with which we want to talk. So let's get to how this protocol is implemented. So first of all, what happens is that the chip select pin for a particular slave is set to low. So let's say there are 3 different microcontrollers connected to one, and uh, we want to tell microcontroller number 2 that I'm talking to you and I want you to talk to me. So I'll put the chip select pin of microcontroller number 2 to low. So the microcontroller will know that the master is now talking to me. Then I'll start sending out the clock along with the data so that the microcontroller can interpret whatever is happening. And this is precisely what happens. So the clock is low until I want to talk to the microcontroller, and then we have all the data we're sending out from the MOSI pin and a clock. Now, similar to what the MOSI pin looks like, we can have a MESO pin here which also has data, but the data is being sent in. So this is a full duplex protocol, which means that I can talk to the slave and the slave can talk to me. This is what it means by that. Now let's get to the Arduino specific implementation. This is what we have. So we have 4 different pins provided in a Atmega 328P. Pin number 10, 11, 12 and 13 on the Arduino board are internally mapped to the SPI pins right here. So 10 10 is for chip select. 11 is like so 10 is for chip select. We send out the clock from pin 11, and from pins 12 and 13 we send out the MISO and MOSI pins. So this is what it looks like, and we have the conventional ground which is connected in these breadboards right here. So a common ground, and this is a simple circuit which I have built in Fitzing. So what this does is, if I press the button here, it would switch on this LED, and if I press the button here, it would switch on this LED. Now let's get to what the code looks like for SPI protocol. Before I get to the code, I need to talk about a little thing called interrupt. So what we have is like what we use in SPI is a concept of interrupts. So in case of interrupts, so let's say I have 3 buttons connected to a single Arduino board, and I want to do a particular thing when a certain button is pressed. So I have 2 ways for doing that. The first one is to continuously check whether button 1 is pressed, 2 is pressed, or 3 is pressed, then loop again to check that. But sometimes we might miss the button being pressed. So let's say before the controller checks button 2, I press it and the controller misses it. So the input's gone, which is kind of a problem. So to rectify that, we have interrupts. So what an interrupt does is, the microcontroller keeps on doing its thing, and as soon as button 2 is pressed, whatever the MCU was doing, it stops in the middle, and whatever has been programmed for button 2 is executed. So the code in this case for button 2 is also known as an interrupt subroutine, or ISR, which means whatever will happen when button 2 is pressed is programmed into that. So now let's talk about how SPI is implemented.
Hey, can I ask you a question?
This is code for SPI master.
Am I audible?
Appearance.
Hey,
Okay.
Manav.
So
Hello.
first of all, we
Uh,
set the baud rate for communication with our computer. This has nothing to do with the SPI protocol between the 2 Arduinos. Then we put the SS or the chip select pin to high, so that we can disable slave select in the Arduino. Now this is happening in the setup. So for example, if the pin was, for some reason, I don't really know, but for some reason the pin was low, that would cause problems, right? So in the setup code, we disable this part, then start the communication. This is where we set out the clock cycle. So we set the basically the frequency of the square wave we saw emanating from the CLK pins. We set the frequency here. Then we enable the slave select of that particular like the controller we're talking about. For example, let's say on the SS pin another Arduino is connected. The SS pin is pin number 9. So another Arduino is connected on the SS pin. So for that we have this. We'll set this to low, send out a string. This is a simple function which sends out the string character by character, and then disables slave select, so that the receiver knows that the controller is no longer talking back to me. This is what the code looks like for the master. Now let's talk about what the code looks like for an SPI slave. Now let's start by this buffer, and we have index, and process. So all of these are variables. We'll talk about them during the program. Now, a little thing I wanted to talk about here is the volatile keyword. So I thought, why not cover this? A volatile keyword basically tells the compiler not to change the variable into something else. So for example, let's say I've written another program. Let's say I'll give a small example so that I can actually describe what this looks like. So for example, I've written a program here. This is a small code snippet, says int s is equal to, let's say, 1, and we are doing something here while s. So what the compiler does is, it looks at this part, it thinks that s is equal to 1. So what I can do is, I can always, instead of each time coming here and comparing, I can just set while true and go do my thing. But sometimes we don't really want that, because sometimes the compiler might not know that the value of this is being set by an interrupt and is being changed. So to explicitly tell the compiler, we are using the volatile keyword, so that we can tell the compiler that this variable might be changed by some source that you might not know or recognize. So please don't replace it in line. So we have the buffer and the process. Now in the code, this is the standard serial.begin. Now we have to set the meso pin to output, so that, like, so the master in slave out pin, right? So that is set, has to be set to output. Turn on s. So now what we do is, we turn on SPI slave mode, so that we can, now what is happening here is, this is a little bit manipulation. For actual details of this, you'll have to refer to the Atmega 328p. Atmega, like, you'll have to refer to the guide to program actually the Atmega 328p. That is, the implementation details go down there. So we'll set the buffer to empty, set this variable to false. Now what this is doing is enabling interrupts for our SPI pin. Now we're going to write the interrupt subroutine, or the ISR. Now what is being passed here? This is the location in the Atmega 328p wherein the interrupt subroutine is stored. So whenever this function is called, we know that we need to go to this place and look for this function. So basically what happens in this function is, we are trying to read from the SPI data register. So this is a simple situation wherein we are reading character by character and storing it into the buffer. And we're setting this variable of process to true, which means that data has been read. Now in the loop, if process is true, reset the process and empty out the data onto the serial monitor that dump the data, and then we'll set the buffer back to 0. So this is what the code looks like. Now I will pause here for questions.
Hi Manav, I'm audible.
Yeah.
So Alok has a question. So question is, when to use UART and when to use SPI. I'm confused. Does this question make a sense?
Yeah, this question kind of makes sense to me, because in a situation wherein, like, no, I think yeah, after thinking about it for a second, so what happens in the protocol difference is that UART only allows me to communicate from one side to another if I have one pin. So if I have TX and RX pin on both of the microcontroller, I can set it up as a dual means. But in other cases, I will have to use SPI, wherein I do not have TX and RX pins. But other than that, I will get into this details of comparison between all three different protocols at the end of my presentation.
Okay, thanks a lot.
Any other questions? Okay, seeing no questions, we'll move forward. So next and the final protocol we're going to talk about is the I2C, or the inter-integrated circuit. Now I2C was developed by Philips in 1982. This is a piece of trivia that I read about somewhere. So this protocol is a synchronous protocol, so obviously it requires a clock, which we have right here, the SCL and the SDA, the serial data line and the serial clock line. So this is what SCL and SDA stands for. So we're sending out a clock here and we're sending out all the data we have. So this is pretty simple in terms of implementation. And in Arduino, if we want to do Arduino to Arduino communication, we have these analog 4 and analog 5 pins which are mapped internally. And apart from that, as we can see in this diagram, these two pins are also lighting up. So in fritzing, when another pin lights up, it means all these pins are internally connected. So we do have SDA and SCL pins right here, but this is for peripheral communication. So if I want to connect another peripheral which is not another Arduino board, I can use that. I can use both of these pins. Apart from that, if I don't know why somebody would, but if you want to, you can also use these, a part of these ICSP headers right here for connections. Now this is what the I2C looks like when implemented in terms of Arduinos. Let's get to the code. So the code is pretty simple. Let's talk about master. So yeah, so let's talk about the master code. So we have wire.h library in case of an Arduino. All we need to do is set the wire.begin. We need to start now. What is this number 9? This is device number 9. So this is another catch in the I2C protocol, that before sending out any kind of data, the I2C sends out a receiver address. So 9 is actually let's say this is actually a hexadecimal address which has been converted by Arduino to a simple number for increasing the readability. And for this, for actually seeing, let's say I have 4 different Arduinos connected and I want to see the address for all of them. So wire.h actually has an example, which is the SPI discover example. So if you run that example on your master, it will read whatever I2C devices are connected and will fetch you the addresses in terms of numbers and hexadecimal codes. So this is what is happening here. So wire.begin transmission to device number 9. Then we have wire.write send. Basically it sends out the character X. X is the number here in this, actually in the context of this program. And then this is, we're going to increment the value and end the transmission before that. So it will send out a number, close the data line, increment the value, then this will happen again. So this is what the master code looks like. Let's look at the slave code. Appearance to presentation mode. So we have the wire.h library. Now what we are going to do is we are going to set the address 9 and start the I2C communication. Then we are going to define this one function of wire.onReceive. So what this does is, as soon as data is received, it will call another function or maybe a variable. This can be a function or a variable. Receive event can either be a function or a variable. You can see it is defined as a function here, which will, as soon as it sees some data, it will start reading from it. So in the loop, all we have is if the data is 0, blink the LED for 200 microseconds. If the data is 3, that is what it looks like. So these are all the communication protocols that we're going to talk about today. Now let's get to a little bit of what is the difference between these protocols, and then I'm going to end my presentation. So let's just summarize these protocols. So we have our master device, and all our peripherals connected to SDA and SCL data lines. So this is what it looks like. In the SPI protocol, we have a clock, and a clock for 3 devices, separate chip selects for all the devices, and a MOSI and MISO pins for all the devices. In case of UART, we have a TX to RX, TX to RX, TX to RX pin, and a common ground. I did not show a common ground in these because it seemed cluttered. That's why. But we do need a common ground in all of these protocols. So let's talk about a little bit of difference. UART communication happens between one-to-one devices. I2C is a simplex communication and SPI is a full duplex. So what simplex means is that I can talk to the slave and but if I tell the slave to return data, then only it can talk back to me. Otherwise, it cannot. So in case of the SPI protocol, all this happens simultaneously. So the slave talks to me on a different data line and I talk to the slave on a different data line. So all this happens simultaneously, hence a duplex protocol. And UART is asynchronous. Both of these are synchronous. UART requires 2 wires, which is these ones. I2C also requires 2 wires, and SPI requires 4 or more wires depending upon the number of chips we have. This is the average data speed amongst all these protocols. So as we can see, the fastest one is SPI. That is simply because we have separate data lines and like the clock is being sent out and everything. So that's that. In UART, in the new microcontrollers, we do have acknowledge pins. In I2C and SPI, we don't have any acknowledgement, so we don't have any means of checking if the data is actually received somewhere. Both of these consume medium power. SPI can run on both low and medium power situations. So if I have a certain use case that, let's say, a microcontroller is going to be mounted into a device that is going to be used for, let's say, 30 days at a stretch, and I want to preserve the battery. So Arduino and a lot of microcontrollers have sleep mode or low power mode built in. So SPI supports that mode and can actually work in this low power mode. And the final is the distance of the wires that is supported in all these protocols. So this is it from my side. Thanks for having me. The floor is now open for questions.
Thank you, Manav. I have a question. So you discussed about the interboard communication. So
Yeah.
my question is for intraboard communication. Like if I have a ADC and I want to I want to use a external ADC for on my board and I want to connect this with my microcontroller. So what do you think? Which protocol I would you'd
So
suggest?
for that, I think we should use SPI, since SPI provides both, like it kills 2 birds with 1 stone, because we need a good sampling rate when we are using ADC. So we need a fast protocol. That's why SPI, and also we need a means of duplex communication. So I should be able to send data to the ADC and ADC should be able to send the data back to me. That-
Okay.
Does that answer your question?
Yeah.
So,
So
Yeah,
yeah.
I have one question. So, Manav, can you go back one slide?
sure.
So I read this acknowledge pin in UART. Can you talk more about this? What is acknowledge pin? How this is work and things like that?
So we have on modern microcontrollers, we do have an acknowledge pin, which is an ACK pin. So this often depends upon the implementation, but as far as I can remember, what happens is that when the acknowledge pin is set to high, that means the other microcontroller is cleared for sending data. This is what I remember actually. Is this correct? I'm sorry for actually not remembering these details.
Actually, even I have not used any kind of acknowledgement on hardware level. So
Yeah, but actually I read about this pin in modern microcontrollers. That's why I added this, because I thought somebody might point out that it has that. So as far as I can remember, this is what the implementation looks like. That if the microcontroller on the other side sets the acknowledgement to high, that means it's cleared for data transmission and it can actually send data back to me.
So it could be like the classic RS-232 protocol, which has
Yeah. Similar to RS-232. Yes.
request to send, clear to send, ring indicator, data
Yeah.
terminal ready kind of things.
Exactly.
In which you have framing error and all. I guess you all are talking about that topic only.
Sorry?
Basically, if the acknowledgement is not done correctly, then you have a framing error. I'm not sure. I think you guys are talking about this only, the framing error thing.
It was more about Manav mentioning that some microcontroller have a dedicated pin which can provide acknowledge, but I'm not really sure how that works because I've never come across. So I just wanted to clear that.
Yeah, I've read that this is present in, like, this is not present in microcontrollers that we actually use for prototyping. So Arduino does not have that. Some TI MCUs that we use for prototyping do not have that, but the MCUs which are in industries and actually need something of this sort have this pin in them.
Okay.
Any other questions?
Yeah, Manav, I have a question. Like, uh, look, there is a scenario where a component is connected to microcontroller with the using some protocol, and the other thing, that same component is memory mapped with the microcontroller. So which way is uh, um, which way is good to connect the same component?
Didn't get your point. I think what you mean is that I have the address of the peripheral that I'm connecting. Is that what you mean?
Yeah, no. I'm saying that I have a component like A is a component, so I have to connect that component to microcontroller. So so there is a scenario. And first, I'm using a protocol like SPI or something I2C, and the second scenario is I'm memory map that component to the microcontroller. So which way is good and which you prefer?
Mm, so I'm not sure about this question, but I think we should use I squared C since we
What
have a
again?
yeah.
What was the question?
The
Question.
question, yeah, Sivan.
Yeah, so the question was if I want to connect a component A to the microcontroller, so which protocol you prefer? Like, so you prefer the protocol or like SPI or I2C, or I can directly memory map to that to microcontroller. So which way is best?
So that is not in your hands. That is in the hands of the manufacturer or the company which is making the protocol and how they are exposing it. So if, for example, temperature sensor are available in I2C interface, in SPI interface, not sure, maybe in UART interface, or some are just like exposed pins you can connect it to GPIOs. So that is not actually something which we can control. Number one. Number two, a classic way of implementing some sensors like are there is a sensor and there is a small microcontroller on the board, and you can define how you want the data out. So in that case, it's up to you, but it's mostly I2C or SPI, depending on what data that you are looking for.
Okay, thanks. Thanks, Anand.
So I'm still waiting for more questions.
Is there any question on YouTube? Can someone check?
No, there is no question. So, Swarim wants to ask a question. I have a less relevant question. Is CAN good for small scale IoT? I think
I have to
so.
be very honest. I have not researched a lot about CAN protocol, so I am not the right person to answer this question.
So, Ayan, would you like to answer this?
Yeah. So CAN is mostly used for automotive applications. It's controller area network developed by Bosch. Regarding small IoT, I'm not really sure what exactly you mean by small IoT. Are they constrained devices? If yes, then definitely not. The CAN is not meant for constrained devices. If you want to have some sort of industrial level machine to machine wired communication, because CAN is also wired, then a better option is Modbus compared to CAN. Hope that answers.
I'm completely agree with that. Modbus instead of CAN. So, any other wants to speak on this? Maybe Mason.
Nah, just uh, the talk was really great, Manav.
Thanks.
Um, it was just a really good basic talk. I think most of ILUG-D peeps needed this, and they can check the recording of this talk on YouTube. It was a great talk.
Thanks.
Yeah, it was a great talk. Thanks. Yeah. Also, can you just turn off the live stream and just tell us?
Sure. Sure.
Sure,
I'm
let me
sorry.
end it.
So let me look.